Hi, everyone. Welcome to the second day. Glad we were able to make it despite the blockades. So the presentation today is by Gal Vishner from ELSTEC and Oria Cohen from the Hebrew University, the ELSTEC Center, and so on and so forth. And they're going to talk to us about neural representations that are supposedly not natural representations. Thanks, guys. Okay, we're waiting.
Okay, so to start the talk, I'm gonna give a quick introduction that's aimed to explain what we call neural representations, what we call natural representations, what we call content multiplicity, and what we want to claim. I suppose everyone here knows what a representation is. What's important for us is the distinction between the physical vehicle and what the content that it represents. We are aware of very different types of representations that we always use. Of course, there are differences between them. Some are conventional, some are dependent on causal relations or structural similarity. But they all care in content or meaning information. We're not going to really say much about any differences between these terms, and they have intentionality, and representations can misrepresent. So let's skip that. What we're calling neural representations is the notion of representation that is at use contemporary neuroscience. So that's what we're going to call neural representation. So neuroscientists often explain things by assuming that there are internal content carrying states. And so it seems they are assuming a notion of neural representation. So that's what we're going to call neural representations. So what do we call natural representation? So maybe we should have called it original representation. That's what we really care about, right? So we're going to just assume that representation is natural if it's not in any way dependent on external cognitive agents. So probably, this is I mean, you're all aware with the terms of original content, intrinsic content, so that's the point. Yeah.
Hey, I'm sorry. Can I just make a suggestion, a terminological suggestion going forward?
Yeah.
Since the term original is generally used pretty commonly for this, and the term natural representation is often used for something else. I would recommend sticking with original and leaving natural for the other, like the term natural meaning comes from Grice, and it means something that's basically due to correlation.
Okay, yeah.
And it's been used in the representation literature.
Yeah, so we kind of stuck with the natural representation because it fits with well, I guess we're arguing against naturalistic theory of the content, so that's why we stuck with the term. But yeah, the original representations would be more correct for what we really have in mind. What we want to claim that neural representation is not original. So I'll try to stick with the term, though. You'll see the term natural representations on the board. But I totally agree. So right, conventional representations are always kind of defined by us, even if they are dependent on kind of objective causal relations or structural similarity. They're still always, in part, at least, defined by us. So the question is, what about neural representations? So basically, the distinction we make is that naturalistic accounts claim that neural representations are not like that, right? They have original content, and they aim to explain what that means, how that comes about, and what is original content, and why neural representations really have that. And what we call pragmatic accounts, which is kind of the less popular view, I think, maintain that neural representations are not original because they are somehow dependent on the explanatory considerations of external researchers. So what we want to do is kind of make an argument in favor of this latter view. And the argument is based on the idea of content multiplicity. So basically, content multiplicity, what we call content multiplicity, is when a single representational vehicle, the same exact vehicle, is carrying multiple distinct contents. So we are aware of this, or seemingly aware of this phenomenon in conventional representations. So the same the same string on the screen, the physical symbols, they have, it seems, two different meanings. And probably the best known example is this rabbit duck figure, which is again one physical vehicle, one figure on the screen that has two different contents. So that's what we call content multiplicity. And what we want to argue is essentially this. It has two parts to the argument. First part is that the notion of neural representations that neuroscientists use allows for and is somewhat dependent upon enabling content multiplicity. So that will Gauss will present this now. And that naturalistic theories of representations cannot account for content multiplicity, which should mean that the notion of neural representations that neuroscientists use is not original representations. So that's the idea, and so Gauss will take over for this part.
So, hi everyone. So as always said, what I'm going to try to show is that content multiplicity is not just in the neuroscientific practice, but actually pretty inherent to how we do it in contemporary neuroscience. I'm going to start with some more schematic examples, and then also give pretty briefly a contemporary example that's been really influential in the field. But I think like the main take homes are already in the schematic part. So the example from contemporary neuroscience is just to show you that it's not us making up examples, that it's really out there. But anyways, let's just start. So in the conventional way of how we think of representations, it goes something like this. I'm going to stick to the schematic example where we present a human, an animal, someone, patches of different colors. So it could be orange or blue as we present here. We record activity from a neuron or a set of neurons, and then we check the spike rates of the neuron. If we see some systematic relation, like what you see here, then often we would say the neuron is representing this feature that we see the systematic relation to. So here it would be color. I already know that you might be coming up with objections that this is not enough. This is just a correlation, the tracking relation, and that's a good point. And this is exactly why we did take an example in a contemporary example, just to show that what we care about is how the neuroscientists treat it. So it's going to be the abstract examples. I'm going to focus on the tracking relation, but the important part is that there are many cases where this is in practice how people treat it. And this is just to show that it can also be continuous in relation if we show more patterns in the middle, same idea. Now, we can already talk about content multiplicity in these single neurons, but it's kind of a niche case, more around the edges. So we thought it's important also to make the transition to something that's been really kind of exploding in contemporary neuroscience, and that's the move to population representation. This is probably just a partial list of reviews from recent years, and so you can very clearly see, I mean, this is just stuff that we encountered. So I think it shows really clear that this is exploding. So this is definitely getting prominence as the main, if not by some people, the only view. So, and here we'll show that content multiplicity is in some ways inherent to the very idea of representation. So let's continue with the same example, only now that when we talk about the population representation, we're looking at the entire population as the representing vehicle. And we do this by considering this abstract, or not, but this neuron state space, where now just each axis corresponds to the firing rate of a single neuron. So now we present our animal with the orange patch, and it would correspond to a point in the space where now the location of this point corresponds to the neural activity of multiple neurons, or like to be a region or anything the researcher records, the entire brain. So this corresponds to the activity of multiple neurons when the animal is viewing this orange patch. So this neuron fires this much, this fires this much. Of course, this is very schematic because we can't really put so many axes on the board. But this is the idea. So all the activity of the population is represented by the point of this point in this space. And for what we're going to show schematically, the shape of the point is going to correspond to the presumed stimulus that we're showing. So here we present the orange patch once, and this is what we get. We can do this a bunch of times and do it a bunch of times for our blue patches. And we'll get these sort of clouds, manifolds. We can find a lot of names for them in this state space. you can already kind of see by eye that there seems to be some distinction between the two in the state space. And the axis which really shows this distinction is what we call the coding dimension. And this is in practice how neural populations do represent. So it's done by projecting to the coding dimension. But it's not, I mean, the first objective is, well, okay, but the coding dimension could just align with one of the axes. So this does happen in very low level cases, but in practice, in many cases, what we see is that the coding dimension is a lot more complicated than that. It really does require a combination of a lot of neurons. So it's not really something that you can say, okay, it's just you're changing the visualization, but it's the same exact idea. And this is really about at least a group of neurons. And so that's an important point. Now, we said we care about the content multiplicity part. So let's just extend our previous example. So we're looking now not at only at different colors, but also at different shapes. And so still the shape of the point here corresponds to the stimulus that we're presumably showing. You can see just in this abstract example that we now have information both about the color and about the shape of the stimulus. And so actually both are represented. Just the shape coding dimension, like coding of shape is done by projection to this axis, coding of color is done by projection to this axis. Now, the crucial point here is that the physical vehicle behind this is still the same population. And what it's doing, it's not representing color and shape. It's not representing color or shape. It's really distinctly representing color and distinctly representing shape. And you can see this, I guess one of the ways to see this is by looking at these two extreme cases that we put for misrepresentation. So you can see that here, there is correct representation of the color and misrepresentation of the shape, and vice versa here, there is correct representation of the shape, but misrepresentation of the color. So if it was really a representation of color and shape, then misrepresentation should just have been misrepresentation of everything. It should have screwed up our ability to talk about that representation, but it really doesn't change the fact that this is representing shape correctly and color incorrectly, same here. So this is the schematic illustration. Just to show you that it's not just an example that we made up, we're going to talk about a real example from contemporary neuroscience. But just before that, notation interlude, we need to extend this notion over time. Until now, I was like saying spike rate very generically, as for example, an aggregate spike rate a few hundred milliseconds after the onset. But a lot of time you'll see graphs like this that show us maybe some moving average window, but now each point on this line corresponds to the firing rate is around this window, or rate is always something we need a window for. So around here of this neuron or this neuron. So 0, for example, would be the time when the stimulus comes on the screen. Now here we're dedicating a whole axis to time, but when we move to our population representation, we have a lot of other axes, so we don't want to dedicate a whole axis to this. But we can put still on the same space, just the points corresponding to all time points now. So now it's not different like viewings of the same stimulus, but in different times. It's just across. It's the same viewing, just multiple time points. And so we can put multiple time points like this, and it would maybe look something like this, or we could just talk about the line that connected all the points and call it a trajectory. This is just important for us because that's how the visualization is going to go. So the idea is exactly the same. Just think that in each point here, you're also going to see points on their trajectories, just so it's clear how these two are related. So this is the example. I'm sorry, by the way, I'm too fast to slow me down. I was just the main point that you take from this is the first point that Oli highlighted, that there is content multiplicity in how people regularly talk about it. And then why this is so crucial, and why this implies that the content is not original content, is what Oli is going to talk about next. So just to give one real example, we're going to discuss Monte et al. The specific question in this study was about the integration of context into the representation in prefrontal cortex. But what's crucial for us, first, I should say that this is a really important example, a kind of a foundational example in the population view. It's something that people have been doing for many years, but it really started exploding after this. So this is only 10 years ago, and it has already more than 1,400 citations. At least last I checked, it might be more. And so a lot of these citations are really about moving to this population view and the methods that they presented more than the actual specific study that they did. I don't remember if I said, so this is in Nature 2013. And the second crucial point for us is that the stimulus that they used is kind of in spirit similar to the schematic example. So we had color and shape. What they have now is these random dot kinematograms, it's called, with just a lot of points moving around. And so it's a lot like in each trial, what you see is just one of these circles. And they have 2 dimensions. So in the standard case, in many studies use this type of stimulus, and people vary the motion coherence, which means how many or what proportion of the points are moving to the same direction, which is usually either left or right. Then everything else is just going around randomly. And so they vary this. This is known as the motion coherence. So you could be very clearly seeing the motion right, then 2 intermediate levels, seeing 2 intermediate levels left, and then very clear motion left. And now they added another dimension, which they refer to as the color coherence. And here it's just that in the standard RDKs that you might know from other papers, then we usually just have everything the same color. Here we have a variation of color to green and red dots, and they just vary the percentage of dots that's in the same color. It's actually just not to make it too easy. It's actually that every frame it's redrawn, but it doesn't stay the same points, but it stays the same proportion of points throughout the trial. And then again, this varies from clearly the green trial to clearly a red trial, and we have 6 levels altogether. So you can already see where I'm going with this, just as we had in content multiplicity with shape and color in our schematic example, this is going to be the same idea here. So this is just to see the paradigm. Our subjects here were macaque monkeys, so we could really record single spikes. And the idea is that on each trial, they had this, what they call the context, which was signaled by the color in the fixation dot. So the color here told the monkeys what aspect of the stimulus they had to use. So it just told them whether they should be responding to the motion or responding to the color. But on each trial, both of them varied independently. And we'll see that the important point here was that actually information about both goes to very high level regions. And they actually showed that the same population is now doing the selection between these 2 streams, but it's not perfect. And definitely throughout the entire paper, they refer to this same population in prefrontal cortex as representing both of these aspects. That's our crucial point. Just to show you the neural representation. So I'm going to start schematically with, no, sorry, not schematically now, with the motion context trials, but it looks very similar to the color context. So this is though from their paper. So you can kind of see the schematic illustration that we did here. The space here is very high dimensional. It's more than 1,000 neurons recorded. So each time you project it already to the relevant axis, and we're going to see each time 2 axes at a time. So here they projected what they call the choice axis, that's the x-axis, and the motion axis, that's the y-axis. And you see here the mean trajectories, what we saw before, 2 different motion conditions. So the darker it is, the clearer the motion coherence is. Filled shapes tell us that it's strong motion to the left, empty shapes, strong motions to the right, or sorry, not just strong. Filled shapes is motion to the left, empty shapes motion to the right, and the color tells us how strong it is indeed. And you can see, so around the time the dots are shown on the screen, there's no real difference between any of these. The monkey doesn't have any information yet about the motion that's going to come on. And then we start seeing things diverge. The crucial thing for us now is the projection of the y-axis. This is the motion information. Let's see if I want to say anything else about it. Okay, that's good. So this is just from their supplementary. This is the projection exactly only on the y-axis. So the y-axis stays the same. Just for illustration here, the x-axis now is the time axis. You can also see it here because the points stay in consistent time from each other. But just if this is clear for you, so now this is the rightward movement. This is the this is the leftward movement. This is the rightward movement. And here we also have error trials. which is really cool. So we see, for example, that whiteboard trials where the monkey actually pressed left. So this line is really because the monkey misrepresented the motion in front of it. So because the actual motion was going right, that's why it's the dashed line, but the monkeys definitely represented it as going left, that's why it's above it. So this is what we see here. Now, actually, we can kind of stop here already. Motion and choice, exactly, this error trial shows that they are related, but they're not exactly the same. And we already have simultaneous representation of both of these on the same population here. But just maybe to show it even more clearly, we'll see that at the same time that's representing motion, we also get color representation. So first, we are now shifting our axis, right? This is just part of a very high dimensional space in 1,000 dimensions. So we shift our axis, still the exact same trajectories. You can kind of imagine them going into the screen. And so the x-axis stays the exact same axis. The y-axis now that we're showing is a different axis, which is already labeled here as the color axis, but we don't really see it yet because our grouping is still by the motion condition. Now we're using the same exact trajectories, just regrouping them and doing the average again. And this is what we get. So this is still the same information, the same time. So really what you care about now is understanding that this and this are the same. It's just showing them from different angles. And now we can see very clearly that this is indeed, it corresponds to the main color axis. Now so now again, empty shapes correspond, I don't remember if it's green or red. But empty shapes correspond to more dots on one type, filled shapes more dots on the other type. Again, color, how dark it is corresponds to how strong this information is. And you can see very clearly the separation on the y-axis really corresponds to this stimulus description. So this indeed shows us that this is the color representation, this is the motion representation, and they're happening at the same time. So that's the take home. We have representation of multiple contents here. We show the motion, color, choice. They have even more things in the paper, and it's done by the same neural population. Here it's a prefrontal population. This is something that became more and more common when people talk about the prefrontal cortex, because there you really couldn't find simple variables that correspond to single neurons that really necessitated moving to this view. But people are now taking it back also to sensory regions and kind of re-examining things there as well. So it's at the same time representing multiple contents. Back to you.
Thank you. Okay, so suppose we've established that neuroscientists do need a notion of neural representation that allows for content. Firstly, I'm going to try to convince you that this should be viewed as a problem for naturalistic theories. And I want to start with really the basic intuition. And the basic intuition is that content multiplicity is weird. And it's weird not just for neural representations, it's weird in general for conventional representations as well. Because there's a sense in which it seems to kind of contradict the nature of being a representation, the way we see it. So I tried to kind of write this in this way. So there's this, as a representation of X, V only represents X. So this might sound a little weird, maybe it's not the best way to rephrase it, but the basic idea is that if V is a representation of X, then there is a definitive answer to what is the content that V is carrying as a representation of X. And that answer is X, and that's it, right? It's not carrying the content Y as a representation of X, because then it would be a representation of Y. It's not carrying the content X and Y, because then there would be a representation of X and Y. If it's a representation of X, then as a representation of X, it's what they call saturated by the content X. There's kind of no room for anything else. So if X and Y are independent variables, then as a representation of X, it's necessarily not representing Y. So I'm not going to do too much, try to convince you of this intuition if you don't share it. I just, I think it does kind of fit with kind of the basic characterization of intentionality as direction, directionality, like direction towards an object. Like if you're directed towards X, then well, that's what you're directed towards as such. You're not directed towards Y. So that's why you kind of think it really stems from the nature of being a representation of X. And most importantly, I think we see it in cases of content multiplicity as well. And that's kind of where the weird part is. Because even, I said that this is a case of content multiplicity, but there's also a sense where, when this is actually carrying the information of this stick, it's really, that's the only information it's carrying. It's going to be a useful representation of this, and it doesn't mean this in some sense, right? As a representation of this, it's not a representation of this, and as a representation of this, it's not a representation of this. And this is probably, best illustrated in this example, right? You can feel it, right? That as, you say that this, the same vehicle represents both contexts, but we also say, and it also seems to be true, that as a representation of duck, it's not a representation of rabbit. And it's really, again, it fits with this basic idea of what I call content saturation, is that, if it means duck, then that's what it means, right? Ducks aren't rabbits, so it's not carrying the information rabbit. If it's carrying the information duck, then that's the information that is being carried as a representation of duck. And if it means rabbit, then it's a representation of rabbit and not a representation of duck in some sense. So that's kind of where the weirdness comes from, because in cases of content multiplicity, we want to say that V is both a representation of X and a representation of Y, but we also want to say that as a representation of X, it's not a representation of Y, and as a representation of Y, it's not a representation of X. And that is weird, right? It seems like it should be contradicting somehow, but we want to say that it's not. So how do we do that? Well, in cases of conventional representation, well, we have an answer to why all these seem to be true, but they don't contradict, and that is because of the observer. So how do we account for these, three things being true? Is that, well, yeah, it represents both of them, but kind of intrinsically, this figure doesn't represent anything in and of itself. You could say that there are maybe objective kind of structural similarities between this figure and images of or instances of ducks, and this figure and instances of rabbit. But objectively, it doesn't represent anything. But we can view it as a representation of a rabbit, and as such, it's only a representation of a rabbit, right? And we can view it as a representation of a duck, and as such, it's only a representation of a duck, right? We kind of disregarded this piece of information. So that's kind of how we can account for these three things coexisting. It seems to be a contradiction. I think you can kind of say that, the observers kind of absorb the contradiction, and you can also say they really solve the contradiction. Assuming you're considering the observers as a community, then you can really see how simultaneously it does represent both of these things, while maintaining this kind of content saturation. So now we move on to the case in neural representations. So, but these three things will still have to be true, right? You still have this kind of weirdness about it that should apply in these cases as well. And maybe it's worth stating with regards to as a representation of X being necessarily not a representation of Y, that there's a practical sense we see it in coding dimension, that if X and Y are independent variables, then generally the coding dimensions are orthogonal. So if you view the data through the color dimension, you're disregarding the shape dimension entirely, right? You get no information like that. So as a representation of color, really not a representation of shape, and vice versa. Sorry. So so how are we going to account for that? Well, pragmatic accounts have a very easy way out, right? We just saw it. The same thing is that you said in a conventional case, a pragmatic account can't say in the neural case in a way, right? It'd say that, well, intrinsically this doesn't represent anything, right? It's not an original representation, although there is objective relations between the firing patterns and colors or shapes. But we can regard it, research regard it as a representation of color, they're essentially disregarding some aspects of reality and focusing on others. And researchers can regard it on representation of shape by, in some sense, focusing on one aspect of reality and disregarding the other. So essentially, it's the same idea that you had in conventional representations. You can somehow apply it here in these neural representations, right? Assuming you allow the observer a role in defining content, you can solve this kind of weirdness, right? The seeming contradiction. And so, but again, this means you have to allow an observer a role in defining what it means to be a representation. So what about naturalistic accounts? So we think, this type of situation causes more of a problem for naturalistic accounts because they can't deal with the observer, and in a way, it kind of makes this weirdness even stronger because they have to say that there is, an intrinsic sense in which the population is a representation of X and not a representation of Y, but it's also a representation of Y and not a representation of X, and both things are happening. So it seems like a challenge. And I'm going to try to say more about that in a slightly more formal way to show that there should be a challenge for naturalistic theories. If we kind of add in this assumption, that if we assume that defining a neural identity as a representation of some content X amounts to defining a mathematical function between states of V and states of X. So I don't know if everyone's on board with this assumption. I think it's pretty okay, right? It's not too strong of an assumption. It's not that important to the argument, but it helps, makes clarify the way we view it and makes it a little clearer. So we're going to assume that if there is a representation that V represents X, then there has to be a mathematical function between states of V and states of X. And using that assumption, you can say the naturalistic theories want to claim that there is something about the objective state of affairs that kind of gives us that function. Right? That function is there in the world. So using that, we can kind of restate the weirdness that I said before. That in cases of content multiplicity, we expect the same state of the vehicle to map onto multiple states, right? So it have to map onto X and it have to map onto Y. It's the same states and that are mapping onto these different properties, right? Different states of the visible content. But if this is kind of the objective state of affairs in the world, then that's not good enough, because this is not, that does not amount to a well-defined function between states of V and states of X. Essentially, this is kind of a slightly more formal way of stating the same kind of weirdness that was listed earlier, right? This is kind of the accounts for the multiplicity part, but that's not good enough, right? That's not a function, right? If each state in V1 goes to two different places, then we don't have a function. This is what nature gives us, then that's not good enough, right? Essentially, if what we have in the world objectively is this, then that's not good enough, because what we need is this, right? We need a function, right? We need nature to actually give us this function between V and X. But if that's the case, there's really like only one way to get from here to here, and that's essentially to make a selection. You have to kind of, in a way, select this relation over that one, right? That's the only way. If that's the state of affairs and you need to get here, you have to select the relation between V and X over the selection between V and Y. And we think this seems to be like a kind of an observer move, right? That you disregard some aspect of reality and you focus on another. And it seems to be especially the case when you take into account that you have to make two seemingly contradicting selections at the same time, right? You have to be able, again, if this is what you have objectively, you have to be able to get this function and you have to be able to get this function. So it needs to be enabled by kind of two different types of selections, which seems to be, seems to, again, be a challenge for to say how this is done in a naturalistic manner. So you're probably thinking that I'm wrong, right? It's not, yes, I know. It's not a challenge for naturalistic theories. They actually do that because I'm kind of not giving them enough credit. Naturalistic theories, it's not just the tracking relations, there's more to it than that. So they could say, right, V is a representation of X because, yeah, 5 to 40. Yeah. V is a representation of X because it tracks X, but it's also, there's other conditions, maybe it's the teleological function of V to represent X, and that's what makes it representation of X. And it also has a different teleological function, which is fine, and that's what makes it a representation of Y. So we have each of the two different naturalistic conditions, it defines two different contents, and everything's fine. And it can be different, different naturalistic theories can appeal to different conditions. Maybe it's not a teleological function, maybe there are different causal mechanisms that that's part of what defines the content. And you have two different causal mechanisms, and each one defines a different content or a different downstream use, right? Or consumer, right? You have two different, and that's what each one of those defines a different content, and that solves the problem for the naturalistic theories. So that would be the objection, and it sounds pretty good, but we don't buy it, and we think that it sounds pretty good because you're sneaking in an observer as you're saying this objection. So the reply is that these added conditions that naturalistic theories appeal to, the best they can do is establish a distinction, but what we need is a selection. So maybe I should say something about the difference between a selection and a distinction. And I'm not sure what the best way to say that, but as a working definition, I'll say that a selection is a yes-no distinction. So there's a basic distinction, this is A and this is B. And there's an added level to that, to the selection. You say, yeah, this is A and this is B, and we want A, we don't want B, right? This is a yes and this is no. The selection is more than a mere distinction. And what is happening in these cases, what the naturalistic theories can do, the way we see it, is the best they can give us is a distinction. Yeah, this is teleological function 1, and this is teleological function 2, or consumer 1, consumer 2. These added conditions, they differentiate, right, the two relations, but that's not good enough, right? It still leaves us with this, and what we need is this, and it's still, the only way to get that is to add a selection, right? If you're looking at this and you're seeing this, then what you are doing is adding kind of the added, let's say, normative aspect, right? The added selection, the added yes, no aspect, right? To get from here to here, you're adding the green yes, blue no, right? It's not there in nature.
But you see both.
Exactly.
So you don't need to say it.
No.
But you see.
Yeah, so I'll leave that to the
Q&A.
yeah. So you need to choose the green or blue, you need this selection, and then you can kind of continue to push me if these are selection theories and they do make a selection. And in a way that's kind of true, right? The naturalistic theories are often presented as kind of a way to select between different tracking relations. So they do kind of say if B tracks these different properties, you can say, well, only this one is function, whatever, and that way it does really, you can say, if you buy into that theory, that it does make an actual selection, right? And yes, no distinction, right? This meets the condition, this not, these don't. And that way it does select this tracking relation and not the others. So that's true in the way it's supposed to be, it's usually talked about. In cases of content multiplicity, right? So here, so there is a yes no distinction kind of line that passes through here. But in cases of content multiplicity, what happens is that two things pass through the theory, right? You have two different relations that go through the yes distinction, and not just a one, and that's not good enough. And I know you don't agree. We'll get to that soon. But the reason, and that's really how we got here, right? we get a mapping from states of the to two different properties, which is again, it's not good enough because that if that is what exists in nature, then nature doesn't give us the function itself, right? The function that we need. And again, there's no justification claiming that the theories make this selection, right? They don't choose one over the other. Yet that is kind of precisely what we need. And I already see that will be kind of so that will be kind of the crux of the argument, right? So I'll say maybe a little more about it right now. So essentially, the way we view it is if you buy into the assumption, right? So I'm kind of answering the question already at the end, right? So if you buy into the assumption that representation really does demand a function, mathematical function, then if you're looking for a naturalistic account of representation, you'd need nature to provide you with that function. But if nature provides you with this, then that's simply not good enough, right? If this is the best nature can give you, I understand that you're saying, we need both of these, and that's fine. Exactly, and I think you need both. To need both of these, you need to have each one on its own, right? You need both of them, but in order, we need both of them, each one on its own. To get one of these on your own, right? It's not given to you by nature, right? It's given to you by selection, right? There's a difference between getting both of them like this, which is not good enough, and getting each one mapping on its own, which is what you need, right? To get each mapping on its own, you need a selection. You need a way to not settle for this. And nature doesn't give you a way to not settle for this, right? You have to have an observer, which is why we claim naturalistic theories of representation cannot account for content multiplicity. And taken together with what Gauss showed that you need to account for content multiplicity, we should conclude that neural representations as they're used in contemporary neuroscience are not original representations.
Hey, Marcin, we haven't heard you for a while, so you keep the fingers up, the rest of you.
I'm not sure I understand what you mean by content multiplicity here and what really you mean by the observer. So maybe it's a clarification question because suppose the researchers leave the lab. Would that mean that the monkey no longer represents? Suppose neuroscientists die or never really appeared because they were just monkeys and humanity did not evolve. Would that mean that monkey ceased to represent motion and color?
Yeah, that's a question about pragmatic theories in general, right? So
Yeah, I think they are flawed in general.
Yeah, fine. So yeah, that's independently of our explanatory practices that mean that
Okay,
there are no.
So and then I see what you mean. So my problem here is that you said that you need a selection, but if I don't understand the point, why would anybody need that in a naturalistic theory? Because you can believe in common causation, right? There's a common cause, right? It's raining, that makes the street wet and me sad. That's not the same thing, but it's the same thing causing both. Why would anybody need to select one if two are happening at the same time?
Yeah, so the difference is that representation is the different, right? It's a special kind of property. And in the first part of the intuition,
Skip intuition, saying what's the argument?
Right. Well, the argument, there are two ways in this. If the argument is the representation is special, and it's special in the sense that it has to be what I call content saturation, right? It's a sense where it is a representation of
claims that.
Do you agree that it has to be a function like that?
Yes, but you might have a function that actually operates on things which are multidimensional.
Right, but
then
it has to map.
function has to map to one.
The idea is that, right,
So
so
you can define a function.
this
between
isn't a
two
function,
matches.
that's it.
That's
No.
not a problem.
But the
I'm
point
sorry,
is,
two arrays,
the point is that this isn't a
two
function.
dictionaries.
Again. What?
I mean, you can have a function that defines it between two populations. You can have vectors, for heaven's sake.
Exactly, but here, you don't have, you have one vehicle. Vectors you take a vector in the domain of the function, right? But here, it takes the one vehicle state And it's supposed, right, this isn't the function, that's the whole point.
No, it could be a function, like you're saying, you could take a scalar value and send it to a vector, so you don't have to have a vector there.
Oh,
But
right,
that's
that's,
not what we're
that's a
talking
different
about.
function, that's not the function you want. If you're talking about the function that stands v1 to x1 with y1, right? That's fine, but that's not the function that that amounts to v representing x. That's a function that amounts to v representing xy. Right, that would be its content. The content, if the function goes from v1 to x1, y1, x2, y2, that is one function, that's fine, and that can capture a relation of content, because it's a well-defined function. But that's not the function you're looking for, right? They want to say that it's a representation of x, not a representation of xy, and why should.
Okay, you're saying that there could be something like a rule or something like that that takes just between a kind of property to a kind of property, right? Something like that.
Yes.
Why wouldn't that be just two different functions going like a common cause? Two different consumers, two different.
Yeah, so that's what I was trying to say, that's not good enough, right? Because
not?
objectively, there are both of them. So
Yeah.
the objective state of
That's
affairs doesn't make the selection for you.
You don't need the selection.
Yeah, so.
If there is streets are wet,
If
and
you
I accept,
accept,
I mean,
yeah.
two different.
I
objectively
understand that, I'm not gonna
different
convince
things.
you, but if you accept that you have to have function, a well-defined function in the world between states of the vehicle and states of X.
But that needs
Then
not
you
be a
get
single
that
one. Why should there be? a
Yeah, we see one, right? What you
We
see?
don't see one, we see two.
Exactly, but we see them, right? And that plays a role. No, because objectively, the fact that there are both of them, both of them exist objectively, means that there's no reason to focus on just one of them, right? And you need that kind of focus. Okay,
Why?
In
Because-
taking your example, you're saying it causes the street to be wet and you to be sad, but you're not saying that the rain represents the wet street or represents you being sad. It's cause and effect is not the same as the representation of something. Like we're saying, I mean,
Maybe what you're pointing to are not really representations.
okay, so that
Yeah,
actually
but-
goes to our
okay.
previous point to say
So-
like
These are just part of the model that you should be talking about.
but that
Not-
becomes,
Part of a vehicle, so it's a vehicle, that's not the representation, that you need to define a representation, you need a task function. You need you need a consumer, you need to answer the hardest question, what happens next? So if there are downstream effects, then we can talk about things. If there's just an observer looking at spikes, there might be no downstream effects. It might be what Shapiro calls junk representation, which is not a representation at all.
yeah, fine, so
So-
what we're claiming is that given that there are downstream effects for both of these representations.
Yeah.
Right, then that still isn't enough objectively to define it as a representation. Because objectively, you don't get one-to-one mapping between states of V and states of X. And that captures the sense in which you don't get X, you don't get the like. the
Yeah,
context
I
saturation.
simply don't understand what you mean. I mean, I simply, you should go ahead because I don't understand your point.
Wear helmets during the coffee break and then continue. We will continue with Corey next.
Okay, so I think I have similar concerns. But okay, so let me put it like this. First of all, I'm not sure that you mean the same thing when you talked about the content multiplicity. Because the examples you used at the beginning were ambiguous, right? The bat could mean this, could mean this, right?
Well,
But the ones that you're
not
talking
that
about,
right, yeah.
that one too, right? It could mean this thing, could mean this thing. It's ambiguous which one it is supposed to mean, right? So versus something the task that you mentioned reminds me a bit of the Stroop task, for example, right? Where you have a stimulus, but it has multiple features. There's what the word says, and there's also the ink that it's written in, right? And that seems like the second type of content multiplicity that you were talking about, where it's not ambiguous. There are just multiple contents, right? That are totally objective, but you can pay attention to one or you can pay attention to the other. And that's what the monkey task is, right? Getting the monkey to attend to either direction or colors, just like the Stroop task.
can you explain
Right.
what way is it different? Like, I think exactly in the street task, yeah, you're attending one, not attending the other, but also in the duck rabbit example, you're exactly like the fact that we can't see both, is exactly you're representing it in your mind as one, or you're looking at it as the other. You're again,
Right.
you have to choose one in both ways. I think we're exactly not seeing the difference between these two cases.
Okay, so with the Stroop task, I can very easily read the word red in black ink and report it's the word red and it's in black ink. I can do both, right? Whereas with the duck rabbit, I can say, if I'm seeing it as a duck, I can't see it as a
It's
rabbit.
not the task that we show.
No, yeah, but it's similar.
But no, the strip task is, well, you can make the case that there's, I think you can say that it's actually, there's different physical states that carry different, that each.
Yeah,
content-
there's
a
different there's more than one content.
But there's also a distinction at the physical level. Right?
Sure.
Whereas in,
I'm not trying to see the difference, but
Okay, well, let me continue then, because what Martin said here with the V here could be vectors, right? And so here's a different kind of example. You can have maps, right? Where the XY coordinate of a position tells you where the city is, and then the size of the circle tells you the population, right?
right, again, you're giving me a distinction at the physical level, right? You're saying these.
Yes.
One physical variable gives you the.
It's a vector.
Right,
I
but
mean,
but
say the same about projections, I think.
no,
Yeah.
but that's not projection, the claim we want to make at least, that this is actually the same physical vehicle, and you can't make this distinction between kind of you, in your example, you can make a distinction at the physical, you can kind of solve the content multiplicity by providing a distinction at the physical level, right? That's a
No,
because
I
they're
mean,
different,
still
because
you're
they're
paying
different.
attention either to the size or to the color, and the other thing.
I'm, okay, so
But it is still different, because.
no, it's not. If it were like the bat example, the exact same physical thing, it could mean either this thing or it can mean this thing, and it can't mean both, correct? Whereas this is saying it represents the location in X and Y coordinates
No,
and also the population.
No.
It's representing multiple
So
features.
Yeah, so if I understand the question, I disagree on multiple levels, right? So first, you're right that the bat is often an biggest example, right? But it could
Yeah.
theoretically be, if I write down the word bat, and you work at the zoo at the bat exhibit, and she works at a baseball
Sure.
team, and I show you the word and say, get me a bat, get me this from your workplace. Then for you, it's carrying the.
No, I understand
So
that.
it's carrying two determinate contents. It's not ambiguous for you, it's not ambiguous for her. And in the sense, it's not ambiguous for me either. It's carrying both of these contents simultaneously,
But
in this particular example, right? But you're right that usually what we have in mind is content ambiguity, which is not what we're going for in the cases in the neural.
I like the map example, let's continue with that
Yeah,
example.
that's just like
But
the,
you're still doing the selection, I forgot what the other thing is, that's not size, but you're doing the selection of what to look at in both cases, and I mean, if you
sure,
didn't know how to read out the map. I mean, there's definitely an observer knowing what it should correspond to.
but what I'm saying is,
No,
it's not ambiguous. It's
No,
representing multiple
but-
things, but it's not ambiguous what it's
Relative
representing.
is a readout, but the question is, like, what defines intrinsically which readout you should be using? I mean, there's.
We can.
We
going.
have 8
Yeah.
minutes,
Yeah.
4 questions. Lot them. You go
I
ahead.
didn't finish my answer.
We'll probably continue talking about the same area. Wait, David, that was a great talk and very interesting discussion. I have kind of a worry from a neuroscientific perspective. So, okay, I'll make it very simple, just to make sure that I understand what's going on. So, according to what you said, let's say I have 2 neurons in the brain, and one corresponds to color and the other one corresponds to shape. So in that case, you would say, okay, that can be an original representation. But no,
I mean, yeah,
like the argument for content multiplicity isn't relevant there. But no, let's say that I kind of turn the matrix around and I say, okay, so what represents color is neuron 1 plus neuron B, and what represents shape is neuron 1 minus neuron B. And then you would say, no, then that cannot be an original representation.
well, I think this would be exactly our argument for why the content multiplicity should be taken also for the other cases. I mean, we're saying like, let's use this case, and now do we think that just by doing the matrix, the transformation, we're suddenly getting at an intrinsic representation? We don't think so. So, I mean, we're kind of taking it from that exact part to that. So we're like, exactly, if you agree, and I see there's no agreement, if you agree that it does bring us a problem in the content multiplicity, then I think this would be a very good argument to say, like, maybe we should also be thinking about the simple cases too.
Yeah, our view is not confined to these cases.
And that's exactly the reason why, I mean, what you said.
Okay, but I would maybe go in a different direction, and I would say maybe we should go the of flexible. Like, it doesn't have to be a specific neuron, but a vehicle can also be a vector.
Yeah, that's
That-
right.
that's exactly
what-
that, yeah.
That's what we're doing.
So
I
you
mean,
don't
we're not
have
a
two
vector.
vehicles in the case of.
No, because in both cases, the vector is like, exactly, you're taking the same vector, but you're taking different functions out of it. And then the question is, what defines you that you take if V1 minus V2, or in the other case, V1 plus V2? I mean, if both are intrinsically there because of history or a teleological function or whatever it is, then how do you choose, you build this sort of hierarchy that you need another intrinsic reason to take one in some cases and the other in other cases. And we think that here you get stuck. I mean, why, if both are intrinsic to the same degree, then why one and not the other?
I
It's
think,
the same thing about why you choose neuron one.
no, because here the vehicle is the population as well. I think it's not fully appreciated the sense in which there is content multiplicity where it's really the same vehicle. Maybe we
No,
should,
but I mean.
yeah, I just want to make sure it's kind of clear that it's not. We claim that you can make a distinction at the physical level to capture the different contexts, right? Because, well, essentially, if you have, two neurons, right, and one of them, and they each fire independently, that's 2 dimensions, right? So you could take the addition, and that's one projection, right? And you could take the subtraction, and that's a different projection. But there is no distinction. I mean, if I, fire twice and the guy fires once, and you get out of that 3, and that correlates to something, and someone else gets a 1, and that correlates to something else. There are no different physical states that carry these 2 different contexts.
I mean, the
It's the
mathematical
exact-
function is different, but not
It's the exact same physical, no different physical variables, there's no distinction at the physical level. I got twice, she got once. He got a 3, he got a 1, right? So there's 2 contents, and it's exactly the same physical states, right? No distinction at the physical level. And so it's one physical vehicle, and it's one physical state that carries 2 different contents.
And on that positive note, Mayor. And it's just continuing the same thing. So I think that the argument is nice.
Think the what?
But
Yeah,
the argument
Okay.
is good. The only thing that doesn't convince me completely is that I'm not sure, I don't see why you can't say that there is some physical difference in the signals or something that would support the difference in the multiplicity of representation. I'm not. I mean,
Yeah, I don't understand why.
for example, the formal explanation, you're right, but V1 may have different aspects.
Right.
In which case, the different aspects would represent, one would represent X1.
But what do you mean by different aspect? Because if you mean, right,
Different physical features.
right, so that's one way to solve the problem, it's saying that there is a
But
distinction.
you are arguing that there is.
Right.
I'm not convinced, I mean, I think that if you can show that there can't be in this complete.
So in
In
the
the
example I
clapping
just
example.
gave, the clapping
Yeah, in the
example,
copy-
where are the physical differences?
maybe one response is to the, I don't know.
No, but I told you how to.
But that's still in the interpretation. I mean, you're saying one person get it, I mean.
Should take in their interpretation to be non-physical, which is like.
Maybe to the body of the collapse, I don't know, I mean, you count, you were talking only about the counting of how many, left,
Right.
right? But maybe there is maybe there's a difference between, the time difference.
So that
Or the body-
so that's kind of a different objection that was discussed. You would say that if you look more closely at the
Yes.
physical details,
Yes.
you would find that there is no content multiplicity because you'll find some distinction at the physical level that will solve that.
Yes. And so that's one, so I'm just saying it's a contingent. Point. Now, the other point is that I think that the same happens also with what we call original representations. Like, for example, if I give you a visiting card or how it's called, my card, okay? So I want the car to represent me, but if I give you a very fancy one, it also tells you something. Yeah, so I think that also in original,
That's conventional.
in international representations, there is multiple, seemingly multiple representation, which is explained by different aspects of the vehicle.
Yeah, so that's fine, I agree with you.
So I'm just saying that it may be distinction.
Well, it's kind of the point we're trying to make, that they are essentially.
But I mean, but exactly the example that you said, you're giving the same card, but you're like, you rely on the fact that the interpretation is extracting.
There are different aspects, there are different physical features. You know, one feature of the card is, you know, with respect to one, okay, you see my name on it and so on, but the card is very expensive, but it's, you know.
So this is always the same paper and it's just, I don't know, your name is written in a different font and you're saying like a fancy font or a simple font, but then you're saying the font and the content and the name written in the font is actually.
It's the same card, you know, same card, the one here will be the card, but there are two different aspects. So in the same way, if you can show that there is no, as you said before, in response to.
Corey.
If you can show that there can't be a physical difference in the data, then you'll work.
Yeah, so that's what we.
We need to.
That's
The idea is that in these cases, there is no physical, that you can't, attach each company to different physical variables, unlike you know, the examples.
And again, on that positive note, yes.
Yeah, thanks. So maybe this is a stupid question, but it seems that you're presuming that V is a sufficient neural correlate of the representation. But what makes you think that this is really the case? I mean, what if you look at the brain globally, you actually get a physical distinction of two states which just overlap physically in V1 or in V. It seems that would actually, that seems to be a possibility. So you would have to exclude somehow.
So it's similar.
You were referring to different aspects in V, but this would be a different view. You'd still assume that V is sufficient. But now if I look at the brain globally, maybe I actually get a distinction between.
Yeah. So that again, that goes to the objection that it isn't really a single vehicle with multiple. Because when we're focusing on the wrong vehicle.
Exactly, it's the delineation may not.
But, okay, so I think there's, I mean, we have to think about how to best answer that, but the point is that what we seem to want to say and what neuroscience are saying is that, you know, they regard this is the vehicle, right? This particular population of neurons. Where you're going, well, what is the physical vehicle of that representation, right?
What's
so
the
kind
minimal
of already begins to see a disconnect between the notion of representation that's being used in neuroscience and its explanatory effectiveness. You know, these neurons represent. So these neurons are, you don't have to, they are the vehicle, right? Of course, you can appeal to downstream processes to define the content, but now you want to appeal to downstream processes to define the vehicle, which seems to be like inconsistent with the way we want to talk about these representations.
Well, it's not even downstream. Maybe I mean, I don't know. You listed what 8 neurons. Maybe you want to list 150, but I mean, there's someone's
Actually,
is maybe a co-activation.
They aren't supposed to stand for different neurons. That's important.
Sure.
They are all the same set of neurons, and that's different states of the same population of neurons.
So, but the population
It's
could be-
also vector, so each of them.
Yeah, each one is a vector.
Sure, but the population is still relatively small, given the whole size of the brain that you looked at. And so if you looked at the whole.
Yeah.
Then you get co-activation patterns.
Changing the vehicle representation, right?
And I think like, it's exactly diverging saying, okay, maybe the neuroscientists that call this their representation, but they actually mean something else. And
Right.
I mean, we're trying to explain what are they talking about now. And so we can say that there's a different notion of representation, not exactly the one they're using, the one related, but not the same. That's actually either falling to any one of these objections. And we're trying to say, let's first stick to what they're calling it. And they're definitely saying we recorded a ton of neurons. These are representing. What do they mean by that?
For zero. You're giving up, with one.
Yeah, thank you. Something from a different angle about the pragmatic explanation. Okay, let's assume that you're right. So I think there is still also something weird maybe with the pragmatic explanation. Why? Because you say why the monkey, or why I said red or something like this. So the pragmatic explanation is that because it was V1, right? And V1 caused you to say red, and we take V1 to represent red. And now you ask why I said or why I moved my hand, and you said because of V1, it's the same V1, we have multiple representation, and because we, the observer, take it to represent movement. Okay, so I mean, at least from a scientific point of view, there is something I think a bit weird here, because objectively, right, the same vehicle, right, produces the same vehicle produces two different or explain two different actions, but the only difference in the explanation is just the way the observer assigned the content to this representation. So, or no, you think?
Understand where the weirdness comes in,
Because objectively, there is nothing, nothing makes the difference between the, like, let's say two different actions, because the vehicles are exactly the same, okay? Objectively, the mechanism is exactly the same. The only difference is between the two different, let's say, actions is that you, as the observer.
We don't need to say that the mechanism is the same.
This is what I think you say that the vehicle is the same.
Is the same.
So what is not the same?
Of the action is not, doesn't have to be the same. If it leads to a different action, there's a different. It is a different.
No, but
Yeah, but then.
But he's saying it's a different action.
Yeah, but if you say this, then okay, but then it goes. But if you say this, I think it might go back to the question whether you really have.
The examples we gave, it is the same action, right?
All right.
You can show, for example, even in these examples, there was a motion context and a color context, but you can show that the behavior was affected by both representation within each of the context. So the idea is, at least when you need to represent both of them, it's the same action, right? If you need if you need to say to know both the color of the looking at and where it's going, then there's no problem that it's simultaneously represented in a sense.
So last but not least, and we'll try to keep it short, Oli, please.
Maybe there is no answer, maybe it's just the beginning of a new question. So assuming that we accept your argument, which generally I do, and assuming that your answer to the questions of Jens and Meir is in the negative as well, so there is nothing else that we can look at. And suppose that contemporary neuroscience is correct. I mean, this is the place to look for these things. It's not something mysterious that we're still unaware of. So, and suppose that you can show that indeed there is multiple, there is a multiplicity here. So your argument leads us to the dilemma between two options. Either representation is a non-physical idea, or there is no representation at all. Because that's all the other physical possibilities are gone by your argument, if science is correct and complete. So what do you think? Is there no representation, or representation is a non-physical thing? What is it?
You might have different answers.
So I probably haven't thought about that enough, right? The far-reaching implications, but generally my view is pretty extreme in that there is no such thing as original representation.
Good.
Absolutely.
Yeah.
Do you want to change it? Or you're happy with good?
If you change it for other people, I will say.
Okay, so let's thank our speakers again.
Hello, everyone. I go against my nature and I'm already late by 2 minutes in addition to the 10-minute delay. So without further ado, the next talk would be by Lotem Elbert de Rochefort. She's a former student here at the Hebrew University for first degree, second degree, and third degree. She's now at University of Pittsburgh, and she's going to talk to us about, wow, the good, the bad, and the ugly, why some computational models of cognitive capacities are more controversial than others, and I'll skip the subtitle, just let you talk.
Okay, I'll say the subtitle. I'm trying to focus on one specific model, which is the ring attractor model. And I'm going to ask, why does it matter that the ring attractor is implemented in a physical ring? Specifically in the Drosophila fly. So just before I start this talk, to give some general context, we talked on the bus on the way here and how important it is to do work like for scientists. And it's kind of what I'm trying to do here. Like this is the kind of work that I think scientists would be doing if they had more time. So I'm trying to take my time. This is what Corey said. And philosophers do what scientists could have done if they had more time, which I agree with. So it's kind of trying to take this project in a specific direction. And also, if you've heard my talks before, I got some critiques that I'm very too critical of neuroscientific practice. So this is also an attempt to be positive about it. So let's see if it works. All right. So it won't surprise you that we have a lot of different models, computational models in neuroscience. Just to give some short examples, sometimes like models for visual processing. So we can talk about causal models, kind of like in the Marian framework. People also have predictive processing models. The idea is that visual processing attempts to predict future inputs, and we have convolutional neural networks in the area of deep learning, all trying to explain the same areas in the brain and the same computational processing. Also for decision making, so we can have models that argue that people compute values, Bayesian models, drift diffusion models. So there's really a lot going on in the field. We also see a lot of controversy. So just to give 2 examples, I'm sure a lot of you have seen this picture before. It's very famous, and it's work from the DeKalb lab. And what they did is that they took a computational model, a deep learning convolutional neural network model, and correlated activity in different layers with activity in brain areas that can roughly correspond to these layers. And they found very strong correlation, especially if we compare it to previous models. So this became very famous, and it's now a very productive area of research where people correlate deep learning models with neuronal activity. And just now came out this critical paper in PBS, Deep Problems with Neural Network Models of Human Vision, which criticizes these models and argues that they're not actually good models of how visual processing occurs in the brain. To give another example, a very famous paper cited almost 2,000 times by Padua, Shioka, and Desant, neurons in the orbitofrontal cortex encode economic value. They give strong evidence for representation of value in the orbitofrontal cortex, and recently the case against economic values in the orbitofrontal cortex or anywhere else in the brain. Now, these critical papers, they're not finding like a specific fault in the evidence. They're criticizing the general framework and way of thinking about the brain. And that's, I mean, it's kind of odd and also kind of frustrating because the published papers that got a lot of traction, they bring strong evidence from neuroscience. And it's a question like, what is missing, right? Why do we still have this controversy? Despite the evidence that got the original papers published. So this got me thinking, do we have some examples of models that are widely accepted among scientists and what we can learn from them? So there's really very few, like compared to the hundreds of suggested models in the field, but there are some. The first one is the ring model in that also will apply for head direction representation. This is a model that I will talk about today. Another one, Jeffers model for computation of the interoval time difference for sound localization. I'm not going to go into details, just if someone is interested in looking these up. A famous example, if you read Oron's papers, you should know it, neural integration in the vestibulo-ocular reflex. And also something new, signifier chains for birdsong in the HBC, a brain area of certain birds. And maybe you want to say, look, you're saying so few models are accepted and not controversial in neuroscience, but actually we know quite a lot, right? We know there's a visual area, there's a motor area, there's a language area. But I want to say that I'm focusing here specifically on models that try to explain computation, not like just the general function of a brain area, but how certain capacities are achieved. And when you restrict yourself to these types of models, then you have very few that are actually in the consensus in neuroscience. So I think this is a very interesting question to me. Why do these models receive a status of being sound in brains of certain organisms? So these are models that I heard other scientists, like here from ELSE, from the Department for Computational Neuroscience, talk about, and they say, look, these are the models. We found the ring model in the Drosophila fly. We found the Jeffers model in the barn owl. Why do we describe them as found? And I think there are likely different answers for the different models. But I will try to analyze the ring model today, and I think what comes out of it can be informative for neuroscience in general. So just to kind of qualify this analysis, of course, when I ask which models are controversial or not, this is like a sociological, historical question, right? It's clear that acceptance of models can depend on a variety of factors. Luck and timing may be one of them. What's popular in science, which properties are more interesting. But I'm going to put these questions aside for now and try to find other relevant factors. And specifically, I think for models that are in the consensus, I think you will find yourselves that their intuitive appeal transcends social metrics.
Anat said that you have to share screen, so they see.
It's not. I did share. They can't see the screen.
No, we only see the first picture.
It says, like I have the option to stop sharing. So
Gordana, can you see it now?
No, I just see the first picture, the first slide.
Can you see now?
No, it's in presenter view for us. So we can only see we see the slides before the slideshow has started. We don't see what's going on.
Try doing stop share and then try again. So now you only see us, right? You only see the room now? Okay, let's try again. Which one is the presentation mode?
this is the presentation, PowerPoint slideshow presentation.
Let's try to do it here. What about now? Can you see it now? Okay.
Great. Okay, I'm sorry that you missed the first few slides, but like the interesting pictures are just beginning. Okay. So let's talk about the ring model for head direction representation. So the idea is that to navigate in the world, animals need to represent the direction in which they're heading. We could say the direction of their head. So we expect there to be a representation for every possible angle if you're in two-dimensional space, 360 degrees. And we expect head direction representation to have the following features, just by virtue of being this kind of representation. We want representation for every angle. And we also expect to see a single bump, right? So if I'm representing this zero angle, I can also have neurons that are representing 180 degrees be active, right? Because I'm only facing in one direction. We set the bump, the representation to stay in place. So by bump, I mean that, for example, neurons that represent the zero angle are active and other neurons are suppressed. Stays in place when the animal stays in place, head direction doesn't change. We expect the bump to follow integration of angular velocity. We expect the bump to shift according to external visual cues. So these are all things that we want from a model for head direction representation. And generally, we see neurons that are responsive to head direction. And we find them in a variety of animals in different brain areas. So people have come up with the following model, a suggested model for head direction representation. It wasn't made up for head direction representation, but it was fitted to it. And the model goes like this. You have some neurons are organized in a conceptual ring, and you have local excitation. So neurons that represent similar angles excite each other, and you have long-range inhibition. So neurons that represent angles that are different from each other inhibit each other. And with certain parameters, only states with a single bump are stable. So we have a single bump, we have the stability of the single bump when the animal doesn't move. And we can add to this model neurons that represent angular velocity, and this velocity, their inputs can shift the bump on this ring model. If there are any questions, comments, feel free to intervene. Okay.
Looking the direction is relative to the body, to the world, how?
So it's like they're called compass neurons. So it's it's your body relative to the environment, right? Okay. So it's like if you're facing north, you would be at 0, and then if you're facing south, you would be at 180 degrees. But it can also change between environments.
But it's just the head, it's not the body. So when the head moves, when the body stays the same, you still have a move in the body.
Yes, it should be head direction, even though, like, for some animals, they weren't able to separate head and body. But yes, in the animals that it's tested, it's head direction. So if I'm here in this room, this would be 0 and this would be 90 degrees. Okay, and people search for head direction neurons in the Drosophila fly. It's an animal that people love to use in neuroscience. And there's a brain area called the central complex, which has different anatomical structures. One of these structures, specifically called the ellipsoid body, is an actual physical ring. You can see here. And it turns out if you record using calcium imaging from activity of neurons in this ring, it changes. You see a bump that changes according to head direction. So I'll just show you this movie. This is from a paper from 2015. So you see that we can think about this bump as kind of like a compass because it changes together with the visual signal, denotes specific visual property relative to the position of the fly. And we also have some quantitative results.
Clarification, so was the fly actually rotating on the top of the ball depending on how it moves?
It's walking on the ball and then they shift the visual signal according to the way it's walking.
Yes, yeah, so the visual stimulus is being shifted depending on how the fly moves on the ball.
Yes,
Okay.
yes. So the fly is tethered. So when it's walking, it doesn't actually move, but because they can get the information from the ball, they can shift the visual signal accordingly.
Right, so the move is shot from just behind the fly. The fly is actually not changing direction, but physically. In any kind of absolute terms relative to the room, but it would be if it weren't tethered, because it would be moving along the ball in different ways. In reality, it's the ball that moves.
Right, exactly. Yes.
Okay, thanks.
Okay, so and what we get, they did this with 15 flies. We see they use some algorithm to compute number of bumps, very close to 1 for everyone, and correlation of the this is the population vector estimation, population vector average, with the position of the fly is high for everyone, very close to 1, with for a lot of the flies, similar width of the bump, and so not by width I mean like if the fly is pointing at the 0 angle, then a neuron that representing 10 angles will also be a little bit active. So we see a kind of a bump on the ring. So we see a characteristic width of this bump, and also kind of the mapping between this ring and the true position is different for each of the flies. Okay, this is just another example from a bit newer paper, and you can also see here how the position in blue and the population vector average change together and are very similar. And again, you see one single bump almost always, and the bump changes together with the position, the orientation of the fly.
Just in that graph that you showed me, the blue and red lines, that's just recording from neurons in that ring model, in that ring structure.
Yes. Also, people did intervention experiments where they excited another area in the ring, and we see that it inhibits the original ring. So the dynamics support the idea that there's a single bump. And if you do a quick shift of the visual scene, we see that a lot of the time the bump will change continuously, which is also indicative of the connectivity, excitatory connectivity between similar angles. And we also have information about connectivity features in the complex body of the fly, and they are in line with properties of the ring neuron. So these are neurons in the ellipsoid body, and we see that they tend to excite each other. So we see excitatory connections between neurons that are close to each other, and also we see here we also need the general inhibition, so we see excitatory neurons activating inhibitory neurons, which inhibit them back, basically. So there seems to be like a convergence of evidence that these neurons in the ellipsoid body are representing head direction. And so basically, when I talk about this with scientists, neuroscientists, we look at this and we see, like, is this head direction? Should this be controversial? Can we criticize this finding some way? And you just look at it and you see, like, how can it be anything else? Like, I think it's striking. And I don't know, maybe if your intuition is different, I'm happy to talk about it. But for me, these are very convincing results. Which brings up the question, what makes the evidence for the implementation of the ring neuron attractor in the fly uniquely convincing? And I can think of 4 different reasons, which are, I think, all contribute to some degree, but I will focus on one specific reason. So first, we can say the function of head direction representation requires a specific computation. It really constrains the computations that can underlie it. Another thing that we can say is that we just have overwhelming correlational and causal evidence. We can say that we have information about the connectivity, which is information about connectivity being so describing physical properties of the system is very convincing. And finally, we can say that the anatomy allows inference of function. And I suggest that it's number 4. That's actually the relevant property that we should consider more seriously. So I'll just go quickly through these options and try to convince you that they're not that important. So first, the function of head direction representation requires a specific computation. So there are some functions that really heavily constrain the computations that can underlie them, right? So if I want to compute position from velocity, for example, in the vestibulo-ocular reflex, I must perform integration, right? It's just a property of the world that position is the result of integration of velocity. And if I want to detect edges, I don't know if I say we must, but we should compute second derivatives and look for zero crossings, right? So you can say maybe it's just head direction really requires this kind of ring attractor model. But a useful case to think about is head direction representation in mammals. This is in rats, and we also find head direction neurons in mammals, and we find them not in a specific anatomical rings, but in a variety of brain areas. HD cells, all the blue colored areas are areas where we find head direction cells. So what can we say about head direction representation in rats? We find head direction cells, we find angular velocity cells, we find that activity in these cells is persistent and does not habituate in accordance with what we expect from head direction. We find tethering between preferred direction of different head direction cells. So if I change the environment, the relationship between the head direction cells remains the same. But there's no head direction area. There's no ring. There's no specific localized area. There's no obvious organization of the cells. Like we find, I don't know, in a nucleus in the thalamus, 25% of the neurons are head direction neurons and other neurons do other things. We don't find a connectivity. And we definitely don't say that we found the ring attractor in rat brains. Right? I mean, we can say there is this evidence, that evidence, but it's not like, look at this overwhelming evidence. So function constraining the computation is not enough. What about correlational and causal evidence? Correlation and causal evidence is strong, right? I think this is very convincing. This kind of strong tracking of the activity in the ring, in the ellipsoid body, according to orientation. But I mean, this is basically any model that gets published in neuroscience has strong, at least correlational evidence, and we see a lot of causal relations as evidential support as well. So it's not, this is not something that's unique to the ring model. What about connectivity? So looking at this connectivity again, I mean, it's in line with a ring model, but it's not, it doesn't imply a ring model, right? It's kind of very general, not too clear what's going on here, right? We definitely can get from this a strong conclusion that this is the ring model. Just because it's noisy. Okay, so let's talk about anatomy. So in the fly, we can assign different roles in the ring attractor to different neuronal types according to the location of synaptic connections. So we say we have neurons with dendrites in the ellipsoid body, and these are the neurons that represent head direction, and we also have other neurons in different areas that represent velocity, and we have the stimular cells and cells that give visual inputs. So we can actually do this very nice anatomical mapping between different neuronal types and different properties in the model. And also we have kind of an orientotopic organization, right? So it's not, I mean, we could have a ring and each neuron would represent a different orientation regardless of the position. They could be kind of like random, like a sort of and pepper organization, we can call it. But no, but we do see this nice relationship between the position on the ring and the orientation. But why does it matter? Right? Like, why should we care about it? So anatomy is not connectivity. It has little direct causal effect. It has some causal effect because of field potentials, but we don't think it's a very strong causal effect. Why should it matter? Specifically, why do we care that the fly head direction cells are neatly organized, while in the rat they are dispersed in various brain areas? So I think there are three possibilities to consider. First, we can say that it's misleadingly convincing, right? We saw this beautiful ring, we saw the bump, it looks nice. We are convinced, but we're wrong, right? It's just our biases. We like beautiful explanations and demonstrations. And in fact, we should be just as convinced by other cases that don't have this anatomical structure. Another thing you can say is that anatomy is simply pragmatically useful, right? It allows us to observe and manipulate neurons more easily. But I want to say something stronger than this. I want to say that anatomy actually provides an evidential support for function, right? It tells us about the history of the function, which is important when we want to say what neurons do. So again, let's go through this list. Some people would say anatomy should not be taken as relevant, right? It's just our subjective bias. It doesn't tell us actually something new. But it's kind of a thought experiment. I think that shows that anatomy is relevant here, because let's consider that we find a single neuron that responds to head direction in a rat, right? So it may be a head direction cell, but it also may correlate with head direction because it represents some related property, maybe location, and it may correlate with head direction just because of some connectivity patterns, some synaptic changes that occurred without relation to its function, right? And let's say that we have the whole population of head direction cells in the rats that we saw. We can say, okay, this is a functional unit, but it may be part of a more general network that we're just not aware of. And it actually may be two functional units that simply have similar response properties, right? It's very difficult to just from looking at the population of neurons that don't have an anatomical structure to know what the function is. But if we look at the fly, a representation of head direction in the central complex of the fly, it is much less likely that this brain area's general response is incidental, right? We can say, oh, it's by chance that we got this ring, and we won't say, oh, it relates to something else, right? And we can say, like, it's just part of a functional unit, or we should be divided into two functional units. We accept that it's a functional unit, and this helps us draw a conclusion about the functions of the neurons. So another possibility is that anatomy is only pragmatically relevant. And the idea is that it's kind of indirectly relevant. It allows us to get more evidential and causal relations. So I agree that anatomy allows for further experimentation, but I think it's not for pragmatic reasons. It's because we treat the anatomical structure as a functional unit, right? So it's possible, although it's difficult and the methodology is very complex, to view and intervene on dispersed population, right? But intervention is difficult, interpretation is difficult, because we know we don't have all the relevant neurons, and we may have some unrelated one, right? We don't, if we activate some neuron in the rats and we see suppression in another neuron, we don't know, or maybe we don't see suppression, we don't know, maybe we missed a relevant neuron somewhere, maybe the other neuron is unrelated to this population. It's very much more difficult to draw conclusions without the anatomy that constrains this population as a relevant functional unit. Okay, so anatomy allows us to infer function, which is what I want to claim. because the ellipsoid body is a single anatomical structure, we infer that it is a functional unit. And because of topographic mapping of angle to position, we infer the unique function of every neuron. But are such inferences justified? And I think they are. I think anatomy is indicative of longer time scale historical processes such as natural selection, which is relevant for an etiological function, right? It does historically, this thing has come to be a unit that has a specific function. And it also usually conserved between individuals in ways that sometimes connectivity isn't. So just to bring in some philosophy into this, there is a lot of discussion about the relationship between structure and function in evolutionary biology. I can recommend a fantastic book by Rose Novick that just came out. So basically there's debate. Does function lead to selection of specific structures? Do structures constrain the type of function that an organism can develop to have through evolution? But I think regardless of this debate, what it demonstrates, regardless of who we accept as right in this debate, is that the anatomy and function are strongly connected. And specific structures are indicative of the history of the organism. And through that, they can indicate specific functions. So just to quickly consider two possible objections, we can say anatomy is just a proxy for connectivity, like it convinces us, but just because we think, okay, it indicates something about the connectivity. Okay, so I agree that they are related, but what happens when they come apart, right? So connectivity changes during the lifetime and differs between individuals. It's more fine-grained. So for example, we can think about what happens if a neuron in the ellipsoid body in the fly doesn't fire in accordance with the model, right? Or doesn't represent head direction. I think we would still take their function to be head direction representation, right? We would say maybe they are somehow, for some reason, are not performing this function, but we would still take the anatomical structure that they are part of to define this general function. And alternatively, let's say we have a group of neurons in a single individual that, due to some idiosyncrasy, have come to correlate with head direction and have some causal effect. Should we aim as scientists to explain what happens to these specific neurons in that specific individual? I think not. I think that's not part of what we want to do in science. Oh, okay, so I'm close to finishing. Another possible objection, function should not be about, so I said, like, it tells us about the etiology, and because of that, it tells us about the function, but for that, you have to accept that function is defined etiologically. There are other approaches, for example, Cummings function, that define it like it's just a causal role it has within the system, or we can describe forward-looking functions that don't depend on the past, as Gualtiero gives an example of. And adopts the specific view. And I mean, you don't have to accept the function to be etiological, but this comes at a price, right? So it resists the intuition that the anatomy of the ring model is informative, and it allows more room for idiosyncrasies, right? In contrast with what I think scientific practice is. And I think, and intuition about how convincing the anatomy is. How does this view fit for the general view of functions in the brain? So I'm actually going against the brain here in this talk, because today it's very popular to talk about population encoding, as Gal and Ori just demonstrated, manifold, context-dependent computation, and say that computation is not localized, right? So how does this go together? We're saying that anatomy is so important and localization is important. I think these two can fit together. We just need to accept that anatomy does have an evidential role, right? So we can have large networks, it's functional units, but they will benefit from additional support, like maybe demonstrating that there are concerns among individuals, saying something about the development, and showing that they describe relevant anatomical structures. And I agree that we can have encoding in populations, but I think it's not an accident that we expect it to reflect kind of tasks that are changing environments and learning. and when we see hardwired representations in anatomical structures, well-defined anatomical structures, this describes functions for stable environments. So if I see this kind of population encoding, this is something that I can say that this is a result of natural selection and a long evolutionary process. It's a result of learning, and it's interesting to think about the mechanism that allows for this learning. And in general, we need to be careful not to overassign functions without stronger support, because then we get controversial models. Okay, so if we accept that anatomy is relevant, what are the implications? For philosophers, I think etiology is relevant for the notion of cognitive function that is used by neuroscientists. You can argue that in principle it shouldn't matter, but I think in practice, what this example of the Ring attractor demonstrates is that it's a reasonable notion to have as a scientist. And for scientists, if you're convinced by anatomy, then you should be convinced by other indicators of etiology, development, genetics, variability, etc. And of course, I focused a lot on anatomy here, and it's helpful, but it's not the whole story, right? What we need is a convergence of evidence. Anatomy is one aspect that helps us, but we also need all the other evidence that we got from experimenting and the Ring attractor and the ellipsoid body. That's it. Right? Thank you very much.
Perfect timing, we have plenty of time for Q&A. Yes, please.
Thanks, that was really exciting. I really like this. But I have a question. So for instance, Padua-Schioppo's model of value representation in the brain was really celebrated for a long time now among neuroeconomists. It's sort of one of the key findings, you know, the way to go forward and so on. So it's going to be very frustrating for them to learn that it's now very controversial, but also it may be frustrating for them to hear your talk, because I mean, it seems that where it's more easily imaginable that for certain functions such as, you know, head direction, representation, and so on, you find anatomical structures that sort of intuitively fit the purpose. It's going to be very difficult, also because it's not so clear how value selection and representation was evolutionarily selected for. It's a very complex function, a very complex task, especially when it comes to really, let's say, a multitude of products or something like this. So it seems like it's very difficult to imagine any kind of anatomy that would fit this kind of function. So does it mean you're suggesting this kind of research is in vain, or what are we going to tell them?
Right, okay, so I don't say that anatomy is necessary. You can do without it. You just need other stronger evidence. So the value literature actually has, it will be interesting to talk about it. It has a lot of controversies because the behavior is not well defined, like the relevant properties are difficult to identify. And the most difficult question of how we should identify states is.
You refer to Padua-Schioppa now, or you're referring to Padua-Schioppa's work now?
Just to the also Padua-Schioppa, yes, but also like there's a ton of writing about value representation. So like there's a lot of unsolved questions relative to value, which is also, so I mean, this is the function kind of question, right? So head direction is easy, right? You know you have 360 degrees, but that's it. And value is much more complicated. So it is. I mean, I think it is much less convincing. I don't like complex behaviors are difficult to explain. I don't have a solution for that, but I think it can be also beneficial, and scientists are doing it to look at historical properties, ecological processes leading to current behavior.
Sure, but again, I mean, it seemed that you recommended some kind of match, if possible, with some anatomical structure of that function, but it's for this kind of function and task, it seems that's almost impossible. So what do you recommend in such a case?
So I think it would be useful, like with the population encoding, you want to describe the mechanism that allows the learning. In that case, so you have what I think, okay, so what happens for like decision making in general, we have this broad, I don't know if I would call it like mechanism, not a physical mechanism, but just this broad capability of being able to make decisions in different cases. But every case, like we don't have a mechanism for like two-armed bandits, right? So we need to, and of course it's very difficult, but we need to kind of try and identify these learning mechanisms. And how implementation allows that kind of flexibility. Does that answer your question?
Yeah.
Thanks a lot. Yeah, I also really enjoyed the talk and agree both about the importance and value of an anatomical segregation and structure, and also the value of comparative and evolutionary considerations for training our, identification of structures and functions, which connects to the point made among others by Luis Pessoa in his recent book that, we really need to spend more time thinking about subcortical structures where there is more anatomical segregation, and it might be easier to do this comparative analysis, across species and evolutionary considerations, like what was the main initial function of these structures that we can identify, and then maybe it can help show light on their current function in different species, even though of course functions can also shift over evolutionary time to some degree. That being said, a lot of important functions are carried out in the cortex, and we do need to, we do want to understand that too. So I wonder if you have any further thoughts about what are we going to do about the cortex. So, of course, everybody wants to also divide cortex, the cortex into different structures. There's like areas, but like how to define areas, that's very difficult to do. And I know there are like current efforts to redefine cortical areas more precisely. But still, like, the cortex is relatively uniform compared to subcortical structures, as far as I understand. So it seems that we're just going to have to rely on these other sources of evidence. As good as we can make it, because anatomy is really not going to differentiate things as well as it does for non-cortical structures, right?
Thank you for this question. So there's also your thought I've been entertaining, which is kind of, I think, more out there. So I wonder what your thoughts are on this. I didn't include it in the presentation. So I was thinking about like a face area, right? So you say the evidence for the face area is that it activates when we see a face, and it doesn't respond when we don't see a face. And that's not very convincing.
There's also evidence for that.
Right, yeah, right. Yes, you're right. But I was wondering if we can think about it from a different direction, and that's kind of like the variability or lack thereof between participants. So if everyone has an area, a specific area that you can localize that responds to faces in the brain, and we see little variability between participants, then and we can have a debate about whether it's exactly faces or something similar, or kind of like people being experts in different things area, but there seems to be kind of like inherent developmental structural constraints there that's relevant. And so perhaps thinking about variability between different people can be a good way to think about this type of questions in the cortex. And I think it matters how conserved these things are between different people, and this can indicate.
Yeah, and your point to development is also very illuminating, because there's evolution and there's development. Of course, those two things also are connected in deep ways, but then development affects function as well. So if we can also bring in a developmental perspective, a neurodevelopmental perspective, to try to see if that helps us identify genuine structures or substructures, even within the cortex where things are much fuzzier. Yeah, good
Yeah,
point.
I agree.
Yeah.
Yeah, thanks very much for the talk. So I was just wondering how much of the work you think that the correlational and causal support for the ring attractor models doing, because it seems like they're comparable models like the cognitive map model, where we have pretty good evidence that place cells are representing places, but there isn't any sort of anatomical or topographical relationship between place cells and the hippocampus and the locations that they represent between that and so on and so forth. And so like, because we have this comparable spatial model that seems like quite well supported, where we don't have this anatomical source of evidence, how much is the anatomical source of evidence giving us in the ring attractor case?
I need to think about it some more, like about the specific example. I will say this, I think so there is interesting work in learning navigation, which demonstrates that if you take like a kind of general model and then you let it learn to navigate in an environment, then you get this kind of grid cells and place cells. So there's a sense in which perhaps we have these place cells. You can say, I don't deny that they represent places, but it's not kind of like a conserved function of evolution, and it's not necessarily a functional unit, like place cells relative to grid cells. I would say maybe it's more accurate to think about them as part of a more general functional unit, in which they have come through learning to play a part. So I think that the idea, which there's also room to better define what I mean by functional unit. But I think that plays a role here. Like it's not just place cells that play this function together. They have a function together with other types of cells. Probably that would be my hypothesis about this.
Yeah, thank you. Just clarificatory questions first. I wasn't sure about in the ring attractor model, right? Each point on the attractor, each point is that, let's say, represents one direction, right? It's not a single cell, but it's the whole population together, right?
It's a slice.
It's a slice, right?
Yeah.
Okay, so when you talk about the but when you talk about the anatomical ring, right, you are talking about a ring of basically single cells, right? I mean, the attractor is not, the ring attractor does not represent, let's say a ring attractor model. It does not represent a ring of cells. It represents a ring in the state space, right? And each point in the state space is
right. You can have many different ways to implement a ring attractor.
Okay.
Right. It doesn't have to be that the stable states are ones where you have activity of one cell and the other one is suppressed.
Right.
You can have other implementations. Yes. It just happens to be that it's a very nice and clear implementation where the stable states corresponds to the activation of specific cells or specific kind of subpopulations in the region.
Okay. Okay. Now I now just so my question is this: maybe when we talk about ring attractor, right? We can separate the evidence for the attractor and for having a ring, right? Like I mean, you can have all sorts of attractor neural networks, right? And one species is the ring attractor, right?
So maybe like, you can have a line attractor, but you don't need to have a physical line in the brain.
Yeah, or yes, for instance, yeah, or you can have other attractors in which you don't have a line at all, you have separated the attractor are separated.
Mhm.
Between- yeah, so I think what I'm trying to say that it seems to me that the evidence for having an attractor network, right, does not come from the anatomy.
Mhm.
It comes probably, from the fact that it's like almost like the first examples that you gave, like in the VOR or the edge detection. You can say, what else can it be? I mean, it's thought you need some sort of almost short-term memory. And yeah, for this, we need like an attractor neural network.
Mhm.
And then just so maybe the anatomy is good. The anatomy supports the fact that it is a special kind of neural net, attractor neural network. Not that it is attractor neural network. So maybe we should separate here the kind of support for the model. I mean, the anatomy doesn't support the whole aspects of the model, but a very specific part of the model, namely that it is a certain kind of attractor neural network and not other kinds of attractor neural network. I mean, it's a question. What do you think about?
Okay, so yeah, I think I'd be happy to talk about it some more and develop it some more. So I'm wondering, do you think that in the rats, the head erection cells in the rat, they also have kind of a ring attractor network? Because maybe I will.
Yeah, probably not. Yeah.
So you said.
But I think, I think, yeah, I don't know, but I would guess that probably it is also a sort of an attractor neural network. Yeah.
I think what I would say in the rats, I'm sure we have attractors in many networks in the brain. In the rat, I'm not sure that I can say that we have an attractor network specific for head erection. Maybe we have an attractor network that incorporates both head erection cells, grid cells, and Purkinje cells. Or maybe the head erection cells are part of two different attractor networks taking part in different functions. So that's where the issue of a function of units comes in. So that's what it supports. This is a single ring attractor network. And we don't have that kind of evidence, I think, for dispersed neurons.
Okay.
Just a quick. I want to clarify something here. So, for the movie that you showed, right? So maybe I was just confused or not paying enough attention or something, but those neurons were physically oriented in like a ring,
Yes.
right?
Yes.
So that was part of your question,
Right.
right? That it's not just the state space, it's that anatomically they are oriented in a
Right.
ring.
It's think how striking it is. Yes, the
Right, so-
physical space,
Yeah,
space,
yeah.
Okay,
but our description of the state space.
right. So
It's
so
not
you
necessary.
you misspoke when you answered Oren's question then, because Oren was asking if it's the state space that's oriented in this ring attractor, but it's anatomically also oriented as a ring, right?
When you say like the state space is multidimensional.
Like the manifold info.
Yeah,
But it didn't get so.
no,
so
I'm just
it's
saying it's both,
both,
right?
yes.
Right, right.
Yeah,
And
it's both. Yeah, I
Right.
mean, that was my question. Yeah, when people attractor neural networks talk about ring,
Mhm. It's a
networks.
conceptual reason.
Yeah, it's a conceptual ring. It's not a physical ring.
But in this case, it's
here you have
also,
both.
yeah,
Yeah,
right.
that is- yeah,
Right.
yeah. This is what I wanted to make sure.
yeah,
Yes.
yeah.
I guess that's related to what I asked you during the presentation of the graph. So the neurons that were recorded were just neurons in that anatomical ring structure, right?
Yes.
I was just trying to clarify. Yeah, that was it.
Okay, so
So maybe I'll just ask, is there another question? So suppose that neuroscientists are on board and they accept your criticism, what would be your recommendation for future research in those areas?
yeah, so it's I think I'm in the direction of what I answered for Thiago. Look more on variability between people, and we have to have some served areas between people that can be an indication that there's like a functional unit that was selected. And look at development and genetics. People are busy, but I don't think there was a spotlight on how this is important and the role this is playing in determining the function.
So you reckon before I send the manuscript to Neuron, maybe look at these other aspects, even if I have good, strong correlations.
You don't want to get the paper saying how you're wrong, like.
Oh, I guess more of a comment than a question, but I think your example with the faces is really interesting because on the other side, like face area is more prominent for most people on the right side. And on the other side, we have an area that's like, it's pretty recent evidence. It starts being selected to faces, but then a very single region actually transforms it to be, I mean, we knew of the visual word form area that's selected to words. And that's an interesting case where you really have to think about like the evolutionary constraints weren't there to make us have to read. And so it's like, it's interesting that it develops around the same region. Though I think this is also a case where we have to start thinking of, I mean, similar to what degree I recently heard, Nancy Kaminger is famous for discovering the face area. And she recently said that she was very happy retrospectively with the words good tools to just aggregate information across brain. So when she discovered the area like in the 90s, they actually printed out the fMRI of multiple people just going around matching areas visually. And since it was a similar area, but not the same area, and if you don't do any sophisticated alignment between brains, you don't get a fusiform face area. I mean, for most people, it's around a pretty broad region, but it's not the exact same place. So on the one hand, I mean, she was able to recognize pattern visually, but it's definitely not very consistent. I mean, if you do the average without doing a smart average based on functional constraints, you usually will average it out and it'll just be a mesh. Like you won't see any specification. So I mean, it's just extending this and starting to think of more problems.
Well, yeah, I think it's really interesting, and I think it's an interesting question what this means in terms of like how this area came to be, like throughout development. Is there like an evolutionary kind of like effects that cause that specific area? I don't know why it's different for different people, like how like the interaction with the environment. Yeah, I think like
I mean, I'm not sure I understand why you like dissociated from connectivity, because I mean the anatomy I mean, first we have the energy constraint, like anatomy is related to connectivity just because of that. It doesn't necessarily have to be, you can do things that are not super energy efficient, but that's a very big reason why we converge on related structure. And I think at least, for example, for the visual word form area, the argument is that it comes to be in that region exactly because of the connectivity was predisposed to the right type of things. So, I mean, that's the type of argument that people are using there, not the anatomy per se.
Yeah, I think that the two are definitely strongly related. Just like in the example that I gave, I think it's interesting to think what happens when connectivity and anatomy come apart. And in some cases, anatomy, I think, plays a larger role.
Maybe you want to check the chat if there's anyone on Zoom.
Yeah.
No. Okay, so let's thank Jochen again.